Hello everyone, welcome back to Z Physics. Today we are going to be talking about electric current. Now, just to get started, what I would like you to do is have a read through those three statements and see if you can find the incorrect statement. And this will be a perfect time for you guys to pause this video and see if you can find the incorrect statement. And the incorrect statement is A. Current is in fact a scalar quantity. We're going to explain why that is the case in a minute. B. Current is a rate of flow of electric charge. We know that's the case from our GCSEs. And C. An LED light can only flow if the component is connected in the positive to negative direction. Yes, LEDs and all diodes in fact only work when they're connected in one direction, just like my favorite band. Now, how can current be a scalar quantity? Because it has a magnitude, how much charge is actually flowing. It also has a direction, where exactly it is flowing to. Well, let's demonstrate this with a little circuit here, which is very simple. We have a little cell which is connected to a little electric bulb. Now, the current is flowing from the positive terminal to the negative terminal. There are only two possible directions for this current to be flowing. It will either be flowing counterclockwise, or if we switch the terminals around, it will be flowing clockwise. So the current only has two directions in which it can flow. Now this is very different to, let's say, a standard vector, which is, I don't know, let's say a force of, let's say, 5.0 newtons, and this force could be pointing at any angle. Let's call that theta. It could be pointing this way, it could be pointing this way, it could be pointing this way or this way, etc. We get the idea. And the current can only be pointing either clockwise or anti-clockwise in this circuit. So hopefully that makes sense. Now let's remind ourselves what current actually is. The standard definition that you may be asked in an exam situation is that current is the rate of flow of charge. In other words, if I have a wire, the current will be the rate at which the charge in the wire is actually flowing through the wire. How many of those electrons are passing through a given cross-sectional area per second? Every time we're talking about the rate of change of something in physics, we're actually dividing by time. And this is the equation for electric current. In this particular equation, I stands for the current, like so. So this over here is the current, and this is measured in amps. Q, or delta Q, is our change in charge. In other words, let's say in 1 second, how many electrons have passed through one cross-sectional slice of a wire. So this over here is the charge that has passed through. In time, delta T. Remember, the charge is actually measured in coulombs. So I'm just going to put that in brackets over here. The unit of charge is coulombs, and time, of course, is measured in seconds. This equation can, of course, also be rearranged for the electric charge, delta Q. So let's just quickly do that, and we're going to see that the electric charge will be equal to the current multiplied by the time that has elapsed. We can also think about the units of these quantities, and as we said, the unit for charge is coulombs, which is given by AC. The unit for the current is amps. Should we just use the unit signs? Quite often units are denoted with these square brackets in physics, so I'm just going to use them for the unit. So a coulomb will be an amp multiplied by a second. In fact, these are actually the base units for the electric charge. And we can even make a little note over here that the base units for delta Q are in fact amps seconds. Now, talking about electric charge, we must mention something really important. Unlike many other quantities, charge is quantized. Now, what does that mean? If we look at any unbalanced charge, any current, fundamentally, they're all multiples of what is known as the elementary charge, which is the charge of an electron. So let's imagine that in this current over here, if we were to zoom in, eventually we'll be able to see some negative electrons over here. And the charge, the individual charge of each one of these is exactly 1.6 times 10 to the power of minus 19 coulombs. So that means that this electron here has a charge of 1.6 times 10 to the power of minus 19. This one here as well, this one here as well, they're all exactly the same. In fact, the total charge of any system is always a multiple of the elementary charge. The elementary charge is often denoted as just the number E. In fact, this is what we're going to be using in A-level physics. It's one of the constant that is given in your formula and data booklet, and E is once again 1.6 times 10 to the power of minus 19. And every single charge anywhere in the universe is always a multiple of that number. Of course, I'm talking about charge on a slightly more macroscopic level. If you have been studying physics for a while and quarks come to mind, we'll be talking about those slightly later on in the course. Okay, so we know that the total charge is a multiple of the elementary charge, and this number n over here is simply the number of unbalanced charges. For example, in this wire over here that I've drawn over here, have 1, 2, 3, 4, 5, 6 electrons. So essentially it's the number of unbalanced charges, most often electrons, although in electrolytes, for example, it could be charged ions as well. Okay, well, we can also rearrange this equation for n. We can do that now, and we can see that the number of unbalanced electrons is going to be equal to the total amount of unbalanced charge divided by the elementary charge. And this is an equation that we'll often be using in problems. So n over here stands for the number of free charges, most often electrons. So I'm just going to say in brackets over here that this is electrons most often. Del Q is our total charge, and E is just our elementary charge, 1.6 times 10 to the power of minus 19. For instance, let's say that I had a charge of 1 coulomb. My number of electrons will be 1 divided by 1.6 times 10 to the power of minus 19. Whenever you're calculating this with your scientific calculator, remember to either use the fraction function on your calculator or just use brackets, because you don't want the calculator to think that this 10 to the power of minus 19 is up here in the fraction. It has to be down there. So 1 over that number will actually give us quite a high number, which is 6.25 times 10 to the power of 18, and because I'm just using two significant figures, I'm going to say that this is equal to 6.3 times 10 to the power of 18. There are no units in this case, this is just the number of electrons. So if I have a charge of 1 coulomb, I'm going to have 6.3 times 10 to the power of 18 electrons. This is a humongous number. However, luckily, electrons are very tiny. And this is how we can calculate the number of electrons. And let's just summarize what we've been discussing today. I've got a little snip of the OCR Physics A specification. If you're doing a different exam board, chances are the specification is very, very similar. But just to recap, electric current is the rate of flow of charge, and we've looked at this formula over here. We've talked about the Coulomb as the unit of charge. In fact, we've even gone further and looked at the base units of it. We talked about the elementary charge E being 1.6 times 10 to the power of minus 19, and we also said that the net charge on a particle or any object is quantized. This actually means that it's a multiple of E, like so. If there are any questions, guys, please feel free to drop a comment, and I shall see you in the next video.